Okay, well then. Ha. Hi. So, well then, welcome to the lecture Distributed Data Management and Distributed Databases. And, fängt ja wieder gut an. And first, some organizational issues. We're going to have this lecture Thursdays, 10:30 to 1 o'clock, 1 p.m. And the reason why we do it a little bit longer is because we do have integrated exercises in this lecture. So there will be no small exercise groups. There will be just the longer lecture with a exercise integrated into what we do. So how many of you did already take lectures with EFIS? Some of them, I see. So many will know the detour concept. Detours are parts of the original lecture, of the actual lecture, that allow you to get deeper into stuff, right? Might be historical reasons, design decisions, why something was made in a certain way. Might be roads that researchers or developers took that are not what is usually considered to be the golden road, but that also works, or there were alternatives, valuable alternatives, where we can discuss some of the design decisions or some of the issues or the disadvantages that current approaches have, but can also be how to work with certain software, how to do certain things, right? So practical exercises. We have like 15, 16 people. That calls for oral exams, right? So during the next free time, we will do oral exams, and I will offer towards the end of this lecture series a couple of dates that are kind of like randomly distributed over the spring, the summer break. And you can then align the dates with your other exams that you have to take, and then there will be a date for everybody, right? So we will make it fit somehow that you don't have all the exams in one spot or at one date, right? But that you can stretch it a little bit and then prepare for each lecture individually or whatever you have to do. Good. Topic of this lecture is distributed databases or distributed data management. I will tell you a little bit about what is important in distributed data management. We will go first into the classical distributed data management part. We will look at peer-to-peer systems. Was during the 90s, during the early 2000s, that was all the rage, and many of the techniques that were used in peer-to-peer systems are still here, right? So this is more about the underlying technology than about the actual peer-to-peer idea, and the algorithms that were used for distributed commits or distributed synchronization. And all these algorithms are still intact. They are still used on a daily basis. Many of them have actually occurred in a new disguise. This is the whole new SQL or no SQL area. So I will also show you some systems from that area and how they are built. And finally, we will look into cloud storage a little bit. And cloud storage is all the latest things. And also a matter of distribution, right? So for you, the cloud is a logical one-stop, right? But in reality, it is rather distributed over several machines, sometimes over several continents, to make your data safe, right? And so we will talk about concepts in cloud storage too. Today, I just want to give you a short introduction of distribution of data and how to deal with that data, how to work on data in a distributed setting, in a distributed scenario. The lecture will be in English, as are the slides. In the exams, we can do any language you like, given that it is English or German. Well, maybe we can do Spanish, yeah. Then I'm lost, but Jose is not. So whatever you feel like. So that should not be a problem. I brought some literature, and there's some standard stuff. So, for example, the principles of distributed. Oops. The principles of distributed database systems of Tamayasu is quite a good book because it shows the basic idea of distributing data and of synchronizing the processes on how you deal with the data. Then we have specialized literature on peer-to-peer. So peer-to-peer Netzwerke is a German book. If you want that, peer-to-peer systems and applications of Ralf Steinmetz is an English book that collects different angles on the peer-to-peer topic, from data management issues to how to deal with the users or distributed reputation-based systems and so on. But many of the stuff that we do, especially the NoSQL stuff, is pretty new and is pretty not yet encoded in textbooks, right? And very often you will find that many of these systems are proprietary systems, right? That are used by some company. For example, Amazon uses the Dynamo technology or the Dynamo system, which is nothing but a peer-to-peer system on steroids, right? So it's kind of like heavily optimized. But it has exactly the underlying topology of the core ring, right? And of course, this is not something that is static or that is, like a classical database where everybody knows how it works, basically. But there is a lot of implementational issues and a lot of things that have been designed for a specific purpose that is needed by the company, right? So I will point to research papers on that. I will point to, we will go into depth there. It's not yet textbook encoded, but for the basic distribution parts, these are kind of like very nice books. So let's get, any questions so far? Hi. Any questions so far? No? Just that I get an overview. How many bachelors do we have? Do we have bachelors? No, we don't. So all masters. Okay. Computer science masters? Business informatics? Okay, good. Very well. Then let's start with the idea of distributing databases. And you all have heard, since you're masters, you will all have heard relational databases, right? Relational databases 101 is one of those courses that occurs in every curriculum in computer science, right? Databases are a groundbreaking technology that are at the heart of every system that you use basically today, right? So there's a database, even if you just have a website or something like that, think about LAMP or something, there's a small MySQL database or whatever, right, to store things. And relational databases are not a novel technique, but basically they have been developed since the end of the 60s. There were different paradigms, and at the latest, in the 80s, the commercial success was there. The first Oracle system came out, I think, 78, right, or 77. And from there on, it's just a big share of the market. And the classic application of these relational databases and why it was so successful and still is so successful is the data management in kind of bookkeeping systems, right? So the early customers were banks, financial institutions, insurance companies, right? That had a very clear view on what they wanted to do. They wanted to keep track of the customers. They wanted to manage funds, right? Assign funds here, money there, transfer of money between accounts and so on. So everything was very clear and everything was very nice. And then when they looked at what they needed to store, they saw the possibilities of things getting bigger and things getting more, right? And at some point, the idea that you really have to manage huge amounts of data became prominent, right? It was just about scalability. Database is a matter of scalability. And if you look into the research literature, even today, you see that on the top conferences, I don't know, 90% of the papers are about scalability. It's not about new features or being able to do something that has never been done before, right? It's about getting things that are well known, more scalable, more data, faster, better. In recent years, it's kind of like also about security. Data security has become an issue, right? We've seen what you can do with data if you don't pay attention. In the Facebook scandal, Cambridge Analytica, right? Happening right under our noses, and we knew that this could happen, right? If that happens on your bank data or credit card data, you would be less amused. I mean, you can say, well, there was public profiles of people that were voluntarily handing out information, yeah, and so if it's misused, then they shouldn't have given out the information anyway, right? But if your bank account is concerned, you're less than happy, right? And this is kind of the basic idea. And to keep it safe, in the beginning, a central database management system was built, and yeah, in the 70s, 80s, were those big mainframe machines, right? The full basement was full with one big machine, and that was the computer, you know, like that was the database. And all the data, the metadata, and all the processing you did on the data basically concentrated on a single room, on a single basement, usually in some company, right? And if you had to distribute data in a spatial fashion, right? So a bank has different branches, you know, like you have the I don't know, Sparkasse Braunschweig and the Sparkasse Hannover and whatnot, you know, like, and all kind of like the other banks. And they were kind of like independent unions, right? So it was not that all the data was concentrated in one point usually, but they all worked with their internal systems. And if something between branches had to be done, right, funds had to be transferred, that was basically done manually, right? So there was a lot of manual handling of these things. It soon became clear that if you have these distributed settings, right, branches in different cities, in different countries, on different continents, that things became a little bit more, well, diffuse, to say it like that, right? And on the other hand, we had this idea of globalization, the global village, right? You can trade stocks in London, New York, Wall Street, right? No problem. It's all Asia, all the Asian markets, Hong Kong, and so on. Not a big problem anymore. So this idea of distribution of data calls for data integration, right? Because you account here that you get your money from, or that you put your budget or your funding from your employer, your salaries or something like that on, needs to be connected somehow to the stock market in New York, where you, in your spare time, deal with stocks or, I don't know, whatever you do. FedEx or whatever. So this idea of data integration, you have to share data and you have to integrate data, the format should somehow match, was a first thing. Then the idea of resource sharing, right? So if everybody handles a full-fledged database, data processing capabilities and so on, so if every branch has its own IT infrastructure, things can be quite expensive, right? So if you kind of can centralize that, you're not only able to link data because they're in one place, right? But you're also able to keep synergies between the usage of computing infrastructure, right? So if you think about it, right, Asia is, well, the big Asian markets are about 8 hours ahead of us. The American markets are kind of 8 hours behind us time-wise. So if the day has 24 hours and everybody keeps 8 hours, right, then you have the typical first do it in Asia, then do it in Europe, then do it in the Americas, and then you exploit your computing infrastructure 24 hours a day, right, which is perfect, which is what you would want to do, right? So resource sharing. Then, of course, the idea of fail safety for data storage, right? You have this data. What happens if there are, I don't know, disasters, natural disasters, right? There's an earthquake in New York. Can happen, right? I don't know how probable it is. If we go to Los Angeles or San Francisco, it's definitely a possibility. In Japan, it happens almost every day. That some earthquake is there, right, and sometimes there are bigger ones, right? So if your data depends on whether you store it in an earthquake-prone or tsunami-prone or hurricane-prone or whatever area, right, then at some point you might lose your data. And losing data is not a good thing, especially if you think about companies like Amazon, right, that really operate all over the world and that have customers that also travel a lot, right? Reconciling their data and keeping their data safe is very valuable, right? And then, of course, you have certain organizational structures that you should reflect in the IT infrastructure. So to a certain degree, you should distribute the data, given that the local data, right, that you need to work on customers, for example, here in Braunschweig, should be very close at hand. If you need to do some international transaction, well, then you might need to ship the data from New York, which might take time, right? But if you have the customer sitting on the counter, right, before you and saying, okay, I want this now, then you can't say, oh, the data has to be shipped from New York, you know, like that might take a while. Bad idea, but you want it distributed so that it reflects the organizational issues of your company. So the integration part of distributed databases or the data management system is the idea that from an outside perspective, you don't even see that the data is distributed. But internally, it is distributed, right? And that means that this integration process should be very lightweight, right? So there's no need for the customer or for the data analyst or person at the counter to see where the data comes from or how it gets there. It's just important that it's there at the right point in time, right, on the spot. And on the other hand, talking about distributed databases, you basically want that all the features that we have loved about relational databases, right? Transaction management, recovery automatically, right? Or all the security features are basically there, you know, like I don't want to have any disadvantages just because my data resides in different storage areas or in different countries or on different continents, right? And So this idea of integrating distributed data so that from a logical perspective, it looks as if it was a central database. This is the first part of this lecture. This is what we are going to do first. So let us define a distributed database. Distributed database is a database, a classical database system, for all we know, where data is stored on several nodes in some network, right? The idea is really several nodes. It's not just a central node somewhere, and if the central node is down, if the server goes down, right, there's nothing you can do. But there are several nodes, and they might mirror each other, they might complement each other, however you build it, right? But it gives you a certain fail safety. And that means that distributed database systems are real databases, right? The full thing, the full functionality, only with a logical perspective on the data sources, right? Where the data comes from and also where the data is processed. So computing facilities are also a resource. And if you think about business analytics and big data data management, right, today you will see that computing capabilities, computing power is quite a big thing these days, right? And being fast in analytic tasks, right? So if you deal on the stock market, analytics has to be in milliseconds, right? It's really very critical because time is money, right? For other things like decisions on the management layer, decision support, for example, that might take a little longer, but still you have to prepare that meeting next morning, 9 o'clock or something like that, right? And you need to get the data ready, right? And that can take time. In the later part of this lecture, so when we go to the NoSQL parts, we will see that sacrificing some features may actually lead to improved performance, improved security, flexibility of the data management, right? But that is a decision that has to be made, right? What do I sacrifice and what do I get for it, right? And there's always a trade-off. There is this NoSQL is always better because it's faster or something like that. It's simply not true. Everything that you improve needs some kind of sacrifice. And we will make these sacrifices transparent so that you can have an informed decision when you say, okay, I want this NoSQL thing working here, right? So be aware, what does it mean if you use it, right? What don't you have for the sake of improving performance? Good. So let's make our way towards distributed databases and see some of the technologies that are behind. And in relational databases, we have kind of very valuable features in the idea of controlled redundancy, right? This is all the normalization kind of stuff that I was getting on your nerves with in relational databases 1, right? But we did that for a reason, because it is important to have consistent data, right? If you consider a banking application where one branch says, oh, the amount of the account of this customer is $500, and the other branch says, no, it's $600 actually, right? How do you deal with that? This is impossible, right? This is not very clever. So, controlled redundancy, data normalization, data consistency. Then integrity constraints, right? How do you deal with semantic aspects of the data? What is possible, what is not possible? Query languages, sure thing, right? You want to be able to retrieve the data. It's not just about storage, it's not just about getting rid of the data and getting it into the cloud, forgetting about it, but you need to make value, you need to create value with your data, right? So for this you need powerful query language that also allow for a certain type of analytics. Then data sharing. I was saying you are living in a globalized economy, right? And these days, it's not just about this single computer in your basement, but it is about all different organizations in the world working together towards common goals. And the common goal usually is making more money, right? And if you can do that together more efficiently, then please do it. And so you need to share the data. And one of the most important things in databases that only ever occurs when it goes wrong is the area of backupping and recovery, right? If something happens, then you cry out for, why didn't the database do the recovering? And of course, then it's too late. So this idea is very strong, and it costs efficiency, right? If I want full recovery, if I want full backupping, it costs time, it costs money, right? But still, if you neglect it, one day you will wake up and the earthquake has happened or the tsunami has struck, right? So you never know. Well, let's look into the characteristics of databases and compare what we can do in the centralized world and in the distributed world. The good thing about databases is that they are well structured, right? So you model everything that is in your world, that are real objects in the world, right? Often called the universe of discourse, and you model it to such a degree of abstraction that you can work with it, with all the important features that are important for your business, but forget about everything that like you don't need to know, or that is not interesting for the application that you're looking at. The basic modeling defines the structure of the data, right? So simple banking system, you have the customer, and the customer might have an account, right? And then you have some attributes or properties of that account. So for example, you have a number, or you have the current balance, or you have a type, whether it's a checking or a saving account or something like that, and then different business rules apply, right? Very simple, very easy to model. Databases are very efficient in the manipulation of data. So we have SQL, right? And SQL is basically composed of two parts: the data definition language and the data manipulation language. In the data definition language, you take that structure that you modeled, right, and get it into a logical design, plus get it into a physical design. You define indexes over the data, right? You define access paths over the data. And on the other hand, if you need to get the data out of the database again, then you need queries, right? And these queries can be arbitrarily big, especially if you have a lot of data from different sources. Then you need to join different tables, right? Or anybody heard data warehouses so far? Okay, only two, right? So this is one of the things that has also been around since the 90s. It's the idea of companies throwing all their data, be it production data, bookkeeping, human resources data, whatever, right, into one big database. So everything can be cross-linked with everything, right? And of course, the joins that you do in these scenarios over loads and tons of data, often even historical data, like the last 10 years. So how did my workforce efficiency develop over the last 10 years? Questions like that, right, can be asked only if the data is kind of integrated and is kind of prepared for that. But those queries take a lot of time, and if you don't optimize them properly, then you will get nowhere fast. Then the isolation between the applications and the data. So isolation is a very important thing in databases. First, it's in the asset characteristics of transaction management, right? It's the I in asset, isolation. And databases use a lot of technology, concurrency control, right? Technology to keep different users of the same data apart, so that they don't get into each other's processes, right? And if somebody changes something, then the question is, should that change already be visible to other workers on the data, or should you kind of like lock the data down until somebody is finished before some other people may interact with the data, and so on. So the question what can happen and what can go wrong is very strong in that. And on one hand, for the isolation, it might be users working with the data, but far more often it's applications working with the data. Very often automatic systems working with the data. If you think about the stock market, for example, there's a lot of algorithmic trading going on, right? So about 80 to 90% of the trades that are performed at any stock market in the world are no longer manual, but they are automatic tradings that are kind of like done by machines, usually with very high volumes, right? So a lot of the market is in the hand of machinery that might work or might not, right? Scary thought, isn't it? And a lot of things happen if you look deeper into that problematic area of algorithmic trading. But still, right, whether it's a human working with the data, whether it's a data analyst or whatever, or whether it's a machine, whether it's an application working with the data, how they manipulate the data needs to be separated from each other. They need to, the effect of what they do should be exactly the same as if they were alone on the whole database, right? If they were the only people in the world working on that data at that point in time, right? This is kind of the idea. The basic isolation, right, that you're trying to do is only access the data that you really need. Don't lock too many parts of the data that could be useful for concurrently running applications or concurrent users, right? So keep it down, but be safe in what you do, right? If you touch something, nobody else should touch the exact same thing at the same time. And if somebody does, then you need safeguards in place so that some of the anomalies or some of the catastrophic things cannot really happen, right? So there are a lot of protocols and different pessimistic and optimistic techniques that are used for concurrency control. Who has heard databases 2? Okay, not too many actually. In databases 2, so the implementation details of relational databases, we talk a lot about concurrency control, and we'll showcase some of the algorithms, some of the protocols that are used there. So whoever is interested can be done. In this lecture, we will only talk about concurrency control as far as distributed data, as distributional aspects are involved, right? But you don't have to know all the database 2 stuffs before you can see what happens in this lecture. And then isolation also means that you are protected against outside manipulation, right? So the database keeps the data to itself, and nobody else from the outside is able to manipulate these data items. And well, at least in theory, right? There's a lot of security breaches going on where data is nevertheless manipulated from the outside, but of course we should make that as difficult as possible. One of the things that or an example for how this isolation is done is in the architecture of databases, right? You learned that databases since the 70s, right, follow a 3-layer architecture with an external layer where the applications kind of interface with the database, the logical layer where the actual database management system resides and all the different table definitions and the structure of the database is done. And then you have the physical layer. And basically it's kind of like this idea, right? The applications on the external layer, the DBMS on the logical layer, and the physical layer is where you actually store data. And why do you do a 3-layer architecture? Because between those layers, you want a certain kind of independence, right? So we're talking about physical data independence. If we can make changes on the physical layer without the logical layer being affected, right? We talk about logical data independence if we can make changes in the logical design of the database without changing all the applications working on the data, right? So for example, if I add another column to a table that does not affect any of the applications that works on the that currently works on the database. Of course, if I drop a table, right, or remove columns, then that will affect the application. So all these kind of data independences are relative. But still, right, I mean, think if you have a table, typical banking table here with the account numbers and the balances, right, and then for some reason the administrator decides, well, it used to reside on one of the old hard drives, right? And now we want faster access, so we take a new SSD drive, right, and want to move it there, right? And by the way, we also introduce a new column giving the type of the account, right? Then to some degree, the DBMS has to figure out there's a new access path now, right, which is done by the physical data manager. And the applications could also work on this new column now, but still everything that was running so far can just keep on running, right? There's no need now to change all the applications or change everything that was done. Good. Another characteristic of database that we want to transport into the distributed area is the view mechanisms, right? So this idea of a view, of creating virtual tables over the data that is at the heart of your database, right, for different purposes. On one hand, for different conceptions of the data, maybe you need different aggregations, or maybe you need different projections. On the other hand, for security reasons, right? Not everybody should see all the data. Some data is secret. So for example, if you have human resource data in your data warehouse or in your database, then you don't want everybody to see, you know, like the salaries of the management maybe, or you know, like the sick days of a certain employee, right? Because this is none of your business. You should not be allowed to see that. This is data protection. This is data privacy, right? So view mechanisms are one way of dealing with these issues, right? For the application, it's just the same whether a view is used that is created, right, or materialized, or whether the actual data table is used, right? It's the same data that is in the view, only in a different, maybe granularity, in a different state of aggregation or whatever. And especially these different states of aggregation, so this idea of virtual data, something has been pre-processed before the query is actually done, right? This is a typical time saver. If you think data warehouses, right, and don't do any aggregations, then you're no better off than using your traditional relational database system, right? It's all in choosing cleverly those aggregations that will help you to answer a lot of the queries faster, right? And this is what materialized views are basically for. example views for projection. So for example, if you have the original data, that is all your account data with the balances and the type of the account, then you might construct two views and say, well, I want to distribute the saving and the checking view. So saving might be interested for the people handling investments, right? Investment bankers that see, you know, like, okay, how much money is there in some account that could be invested, and let's talk to the customers. And on the other hand, the checking view is your day-to-day money that you use and that you need probably and that you don't want to invest. So why should the investment branch consider your checking account, right? So you just create two views, a saving view and a checking view, and one only contains the saving accounts and one only contains the checking accounts, and then, you know, like, you just see what you need to see by simple projections. Then there was the sharing of data, right? And sharing data in a globalized world becomes more and more important, since you will have many users accessing the data at the same time. I already talked a little bit about concurrency control, all these mechanisms to make sure that the same data is not manipulated at the same time from different applications or different persons, right? Because then something is lost, something is getting inconsistent, right? This is one thing that we especially did in transaction control, this idea of atomic transaction, right? So everything that is part of the transaction has to be completed, or no part of the transaction has to be completed. It's everything or nothing, right? It cannot be that if you have a money transfer, for example, that you deduce money from some account without booking it onto another account, right? Because then the money would be gone. Same thing, you cannot add money to an account without getting it from somewhere, right? So all these things would lead to inconsistencies. So this is the atomic part. Isolated is just the part of people not meddling with each other's data. Good. So in terms of transactions, we have this ACID principle that will be very important for the later discussion on NoSQL, right? Because NoSQL databases, it's simply not true that NoSQL databases don't do SQL, right? Many of them actually do. However, what they usually do is they mess with transaction concepts, because those are costly performance killers, right? On the other hand, they make the database safe. So what do you need? Do you need the full safety? Can you trade the occasional error or the occasional inconsistency for improved speed, for improved performance, right? And those are the questions that we will answer later on. So just to recapitulate, transactions have this idea of atomicity. All operations of the transactions are done, or none of the operations in a transaction is done. Then the idea of consistency. If you have any constraints, integrity constraints on your data, then before the transactions they should hold, and after the transactions they should hold. In between the transactions they can be violated, but once a transaction is committed, the consistency should be safe. Then the idea of isolation. People working on the same data, right, should be unaware of all the other people working on that data, right? So you must have fences between them. You must look at what data is actually used, how the data is manipulated, so that you can build concurrency control. And then finally, durability, right? Whatever happens to your data is persistent, right? Is safe. And even if the database crashes or the earthquake strikes, or the tsunami, or whatever it may be, right? Your data is safe. all the changes on the database have been made durable. This is the idea. If you now have a distributed data management system, you want to maintain all the features, however, in a distributed environment, right? And the question is, can they actually be transferred from this single central point of data view to a multiple location view? And how do I need to change them? What do I have to do? And we will see that some of the issues are rather simple to get into a distributed environment, whereas some of the things that were very simple when you did them in a centralized environment become quite difficult, right? And we have to invest in interesting technology and interesting techniques to actually deal with it. So the area of distributed data management system is kind of like a combination area of databases and computer networks, because the networking aspect, the shipping of data, the transfer of data has direct influence on how you process data and the performance of your data processing, right? And also things like safety, security, and so on, right? Plus some additional advantages that you might gain. So if you distribute your data, you gain a certain robustness, right? I mean, if the earthquake strikes in New York and your data resides in New York, London, Hong Kong, okay, you still have your data, right? If the earthquake strikes in all the different sites, it's first less probable, and then, you know, like if all these sites are destroyed, it doesn't matter anyway, whether you have your data, you have other problems on your hands than that, right? So robustness is one of the things. Then, of course, increased performance, because you can parallelize, you can work on data in different areas, you can localize the processing of data, which also accounts for better load balancing, right? So if you have the different, as I said, you know, like if you consider Asia, Europe, and the Americas as different time zones, right? Then you will have a certain peaks of activity during the day in these different areas, right? Whereas the other two areas lie dormant, right? Reusing some of their resources might actually lead to a good load balancing and to nice parallelization effects. Then the storage capacity might become more scalable, right? Because you can have the data in different areas. But also what you have to see is that replication over different areas, different locations needs more storage than you had before, that you had in a central database, right? So sometimes replication is a way to security or to safety, to fail safety. And then, of course, access to data sources, this idea of having a logical view on the data instead of having a physical view on the data, where you really need to know where the data is located, whether it's in the database in Frankfurt or whether it's in the database in London or New York or wherever, right? I don't want to think about that. I just want the data of that customer, this idea of declarative querying, of declarative data manipulation, right? I don't care what the database system does as long as it gives me the data that I need, the data that I want, right? Good. So you can categorize databases a little bit with respect to the autonomy of each node. So is it really a database that is close to a central database? Or is it totally distributed in a very democratic fashion, so bits and pieces of data reside everywhere, right? We're talking a lot about blockchain technologies these days, right? Which is one of these ideas of totally distributing everything everywhere, and lots of copies keep stuff safe in a way. So distributed ledgers, for example. And it's also possible to categorize them with the heterogeneity of the different nodes. So are these nodes of the same type, or do you have super nodes that are more powerful? How do you then distribute the data? Do you have data that is more important close to these super nodes and data that is less important in the outer areas of your system, right? A lot of things that plays a role when you talk about distribution aspects, right? So autonomy, heterogeneity of the data. The easiest way is kind of like the homogeneously distributed databases, right? So where basically every node is the same, right? Has similar capabilities, has similar data storage capabilities, and there's one database management system to rule them all, right? You just have this single system sitting on top of this distributed infrastructure, right? Managing all the calls, managing all the data. The effect that you have if you have a single database system is that you usually have a globally shared schema, right? So having a single database system managing different data schemas on different locations does not make much sense, because then the integration work that has to be done, right, has to be performed at query time, which is the worst thing, right? If you can do it offline, if you can transform your data in a way that it adheres to that globally shared schema, you are very quick at query time, and this is what you want, at data analytics time, right? Usually the nodes are linked via slow networks, so these network nodes are the bottleneck. Shipping data is expensive, so there's a lot of technologies to avoid shipping data, as much as possible, right? You want the correct results, but you want to ship as little data as possible, because shipping is always a bottleneck, right? And typical examples for these systems are, in a way, the classical companies that are distributed over some locations that have different branches in different cities, and each they adhere to a common schema, right? But each has its own system actually running, and then they can share systems over the internet. Then there are parallel distributed databases where each node is controlled again by the same management system, and again there's a globally shared schema, but this time the networking is done in a high-speed fashion, right? And the database system then takes over all the work for the distribution of the data, right? Load balancing, processing capabilities, data sharing, and all these considerations. However, the nodes have no autonomy whatsoever. It's not the branch managing itself, right? It's the database management system. Okay, we have this big job, and you are doing it, right? It's more like a real management style idea. And typical examples of these are high-performance data centers, right? You know that somewhere in the Californian desert and in Australia and so on, so there's nobody around basically, right? People have started to build huge data centers, usually having their own power stations that are needed, having millions of racks, right, where data is processed and data is stored. These data centers are then used in turn by companies like Google, companies like Amazon, to manage their data, right? And some of the world's biggest data centers are actually exclusively owned by some of these companies, right? But there are also open ones that will just provide services to everybody who needs them. And if you need to compute very fast, right, then using one of these computing center or data centers is usually a good idea, because they really have fiber optic networks, you know, like that are basically amazingly fast in shipping data. Then Then there's the heterogeneous distributed database, where basically each node is autonomous and several database management systems might have to be combined. This happens very often if you have kind of like mergers and acquisitions, right? And you're kind of like getting together the processes in different companies, and each company has developed its own kind of philosophy of storing data, working with data. You know, like some might use Oracle, some have contracts with Microsoft SQL Server, right, or with IBM or whoever, right, and they're all running their own little thing, and the actual integration work has to be done on query time, right? So there's no integration between the node, and there's hardly any shared schema or views. So you have to do that basically at runtime. There's a lot of wrapping going on. There's a lot of middleware solutions, right? Translating things between different sources. And of course, all these things cost time, right? So building a high-performance computing center on such an infrastructure is impossible. However, this is usually reality, right? This is the data that is out there. This is the infrastructures that is out there. So this is what you basically will see in companies. One of the things that is often done is so-called mediator databases, right? I was talking about middleware a minute ago. And this idea of having a mediator or a middleware solution running on top of what runs in the different branches, in the different locations, is actually done quite often. So as opposed to the individual nodes, the mediator is centralized, right? And it structures all the communication and all the exchange between the different locations, right? It provides all the different mappings between the data schemas, right? So there's usually some shared views that are common to the different data, and then a lot of mapping, a lot of aligning is going on at query time. And this is one example for this is for example, in the life sciences, if you have all these biological databases, the drug bank, the EMBL, and protein base, and so on, all this data needs to be integrated somehow, right, to figure out whether there are new drugs that might be working against different diseases, right, or whether some gene is affected by certain conditions or something like that, right? And you need to kind of like figure out what the data is, where the data is, and how to combine it. Then there's the federated database. Federated databases is a little bit weaker than the mediator database, where the mediator cares for all, but there's a central federation node, and the federation node really enforces a certain schema that might not carry all aspects of the individual node schemas or the individual node's data, but it usually selects a certain subset that is common to all, right? And then distributes all the queries and distributes everything. So there's not so much mapping going on, not so much aligning going on in runtime. However, the things you can do with federated databases is usually less, right? Because you cannot get all the data in there. It does not adhere to a global schema, right? Otherwise, the schema would be so complex that kind of like nobody can work with it anymore. And this is what you quite often find in corporate database systems, right? Some of these big corporations that have been built out of several companies, right? Several smaller companies that all had their own system and all need a certain degree of autonomy to work their daily business, right? They install a CIO, right? And the CIO has this vision of, okay, couldn't we get synergies going if everybody would adhere to blah, and then it works from there. Sometimes works. More often than not, it does not work, but still. So with that, we go into the first detour for today. So this is where you will experience the detour concept firsthand, and Jose will do the detours.
So just relax a little bit. So this first detour has as a goal just to show you some other examples of where we can find this need of having distributed data management systems. And of course, one of them is in science, and in particular in astronomy. Just think about the kind of data that they are using, image data, for instance. So they are running on multi-terabytes of data, and the truth is that this is only going to grow as they get into more sophisticated instruments to actually look at what is out there, as they say. So what is particularly interesting about this data is that it's highly dynamic. So that means that whatever you do to try to index this data that you're collecting, you have to be aware that it changes quite often. So it's not just that you are collecting some data and storing the data somewhere, but it's about storing it in a way that is in a structured fashion, because you want to make some decisions with this data. You want to decide what is happening, what are theories that may be interesting to explore. So, and the truth is that you have a bunch of different types of data. So you deal with images, true, but you have time series, you have papers, a lot of papers dealing with a lot of issues that are very interesting for the astronomy guys that are looking around what is happening there. So you need to provide, as a key ingredient as well, this idea of data provenance, and that's basically means that the guy who's looking at some data is interested in tracking back where this data was collected, when was collected, by what kind of instrument was collected, why it was collected in that way, because they have to build on some theories to carry on some other experiments. And this is a fantastic example of where you can find the need of a lot of distributed data that has capabilities of the distributed management systems that we just talked about a few minutes ago. Another excellent example is what happens in the European research of nuclear research in Switzerland. I don't know how many of you have looked at this Large Hadron Collider, but basically this thing here is being used to generate such amount of data to prove a lot of theories that you can't afford to save everything. So what they do is that they have some mathematical models in which they know where very likely they will be able to find proofs or disproofs of these theories. And if you look at the numbers, petabytes of data, and this is from 2012. So today you can imagine they are very likely in more than just petabytes of data per year. And the truth is that, again, it is not just getting this thing to generate the data, but how do you actually store the data? In which structure do you store the data so people can actually work on this data? It has to be distributed. There's no single machine that can actually store everything. And this is why one of the main motivations of looking at distributed databases systems. On the other hand, and this is typically the case of, especially in the US, when a lot of research has funding from the military agencies. And if you think about it, I mean, we can use as a simple use case the US. So they have a presence, military presence in more than 70 countries. And they are collecting a lot of data. And they come from different sources, sensor data, geographic data, a lot of information that needs to be integrated in a way. And when you think about it, okay, they are collecting different sources, they are located in different countries, and they need actually to be able to highly interact with the data, because people's lives can depend on the decisions that they made, and they usually depend on this data. So how do you do it? So they invest a lot of money on funding research that is capable of making these systems scalable in a way. So very similar to what we do when we just go to Google and just type in something there and we get results very quickly. Here again, the challenge is how do you structure the data in a way that you can get to make decisions. And you can see that there are many users at the same time in different locations, and they need to make sense of all this space of data. So this is another example of where you need actually these distributed systems requirements. So you need consistency again on the data. You need to be able to handle distributed environments. The challenge here is not that you're just reading information, but you're actually writing quite a lot. So this is really, really challenging. We will cover in some of the lectures why it's so challenging in a distributed environment. And real time. This is a strong requirement. In particular, as I said, think about decisions that might make some people's lives to be in a dangerous situation, or thinking about astronomy again. So where to go to explore the space. You need real-time decisions, and real-time requirements are a must in these systems as well. So what distributed databases can provide to them is this idea of full asset characteristics. This is something that you need in these cases. Consistency on the data, parallel access on the data, and of course durability. This is something that we need in these working environments. This is what I had to say at the moment. I think it's time for probably a break. Yes, I think. And then we will back. Yeah.
Okay, let's go on. So we see there are a lot of applications for distributed databases where you really need it because you have masses of data, and you have different locations where the data is actually created or where the data is maintained, and you have to somehow integrate it. But distributed databases can also be classified with respect to the degree of distribution transparency, right? So what does the nodes share? What does the nodes see of each other? And there are certain types of transparency. So for example, schema transparency. When you design something, is distribution an aspect that you consider, or do you just say there's a global schema and I designed that? It doesn't really matter whether it's central or whether it's distributed in the end, right? But it's just this global schema. Then there's the querying transparency. Do you do it in a fully declarative style where you just say, like, this is what I want, get it, right? Or are there some procedural aspects where you see, okay, it has to be in this node, or it is rather reflected by other nodes, or you have to ask at least 3 nodes to get a vote, which is the correct data item at this point in time, or so on, right? So how is the query built? And then update transparency. Do you need to specify where the data actually goes? Or is that automatically shared? Or, there's a certain distribution algorithm, there's a certain load balancing algorithm that says, right, all the nodes should have comparable level of data, or do you order it in a certain sense? So one node has all the data from A to G, and the next node manages all the data from F to, I don't know, N or something like that, and so on it goes. So the distribution, is it connected to the data, or is it just, like a balanced system? So talking about schema transparency, it's always important that the administrator of the database, or the one who's responsible for the logical design of the databases, is not really constrained by the distribution abstract. So if the administrator has at least the impression of using a single node database, then everything is possible that you can do in normal data modeling, right? You don't have to care about distributional aspects. If you go into degrees of parallelization, all these Hadoop infrastructures or something like that, not modeling it in that way might be a very good idea, right? If you have certain ways how data is combined, and they happen time and again, right? Then keeping that data closer together is a good idea, right? So the semantics of what you're trying to do with the data might strongly influence how you actually view your schema, right? In the best case, it's a thing of the database. I don't care where the data is, right? I want declarative querying, declarative data management, right? I just say what, I don't say how, I don't say where, right? This is for the database to decide. Make it in a way that it is performing well, that nothing is happening, and it's fast. That's all I care about, right? Other things I do not. So if you have that, it's very often coined automatic sharding, right? So the data, the centralized view of the data is distributed to different shards that are coordinated by different systems. The advantage is, of course, that you don't have to care about the distributional aspect. The challenges or the disadvantage that you have that all the semantics of the data is not really used, right? So data that is very often used together by applications might end up in totally disparate locations, having to be shipped every time you combine it again. So joins over different segments of the data might occur very often, which is a performance killer, right? If you do something like that, you have to have a high-speed network. Otherwise, these joins will kill you, right? Good, query transparency. If the user or the application has no knowledge on where the data is actually stored, but all that is managed by the database management system, right? Then, of course, you have the advantages of you don't have to care. Purely declarative, just do as you want to, right? It's just as a single node. However, on the disadvantage side, on the contra side, well, you don't need only a query optimizer, you need a distributed query optimizer. And the problem gets so much harder doing the optimization process in a distributed fashion than it is doing it in a centralized fashion. Given that many of the algorithms that query optimizers use are purely heuristic because the actual problems behind that are NP hard or NP complete, distributing the thing it makes it even harder, right? Does not make it any easier. So the design of distributed query optimization techniques is kind of like very prominent in research, and many people actually do that. For this optimization task, you usually also need statistical data, right? So how much data is there of a certain type, like how selective will a join be or something like that. And you have to maintain this data in the different sites. It has to be current, and to make sense of it, you have to combine different statistics from different locations. Again, data shipping, right? Small data usually because it's only statistics, but still, you need to ship it, you need to consider it, you need to do it, because it is dispersed over different locations. Then the update transparency. Usually as a user, I don't want any knowledge about where something is stored or how it works. And I want that the global consistency is definitely ensured. I update data, right? And the update is valid, right? So I committed it, and it is the database system said, yeah, it fits the constraints. Then distributing it cannot hurt the constraints anymore, right? Or should not hurt the constraints anymore. It sure can, but it should not, right? So advantage, of course, it's as using a single node DB. On the other hand, challenges, You need a distributed transaction manager in order to make it work. So that it does not hurt, right? Same thing here. Concurrency control in one location is difficult at best times. Over several locations, we have a full area of distributed systems, right? And there's a lot of research going on how to make these things consistent and how to make these things work. Ask Rüdiger Kapitza about it, right? He knows all the nitty-gritty of that. So building these things is kind of like very difficult. Well, so what are important issues when you want to implement a distributed database system? First, it's about the distribution as such, right? How do I distribute data? What to put where? And we will talk in next week, we will talk about partitioning of data and sharding of data, right? How do you do that? How do you do that in a clever way? Then we will talk about fail safety, load balancing, and replication of data. That will be the third lecture. Then we will talk about the transaction part, how to do it in a distributed fashion in the fourth lecture. So basically we are trying to work our way from the storage of the data, from the physical layer, to the asset properties, fail safety, distributed transactions and so on, and the recovery, load balancing, replication of the data, right, to what normal databases can do. And the distributed databases that we have today that are in the marketplace do offer some of these features. Very few offer all of these features really, because the features always incur a certain cost, right? As I said, you know, like if you want a full-fledged distributed query optimization, then you are distributedly solving problems that are usually NP hard, right? Does not make it any easier. Will cost performance, needs shipping of data, needs shipping of statistics, integration of statistics, and then you can optimize. So you have to do something before you can actually start to optimize, right? So there's a rather limited scaling, and today's systems rarely scale over 50 nodes. More than 50 nodes is very rare, right? If you look at those computing centers, they use much more than 50 nodes, but they have tricks to do that, right? If you look at the CERN infrastructure for high performance computing, right? The Large Hadron Collider, they scale over much more than 50 nodes. However, they have tricks to do that, right? And we will talk about these tricks. We will talk about how to actually do it. Then today's systems usually offer limited flexibility paired with a high administration effort. And the design decisions that you do, since many of them are semantic, you know, which data is matched together, which data should be kept close by, which data can be distributed or should be distributed more evenly for fail safety or for redundancy. These are usually semantic decisions, and semantics still to a large degree means manual decisions, right? You have to think about it, you have to plan for it, right? The administrator has to actually do that. Moreover, the adding and removal of nodes is rather tedious, right? If it's real world nodes like branches here with companies, it's really a pain in the ass. If it's in big data centers, then exchanging nodes or kind of like adding new nodes is usually a very simple thing. Still, again, you need tricks to do it, to be able to get that flexibility. And then, of course, distribution usually means that you need fast networks, right, to counteract the performance degradation, that you need replication of data for fail safety, for robustness of the system, which means that you need multiple implementations or multiple installations of the same system, right, to carry the same data, which needs hardware costs, right? So you need the best infrastructure, and you need to replicate it. So twofold, threefold, fourfold, just double the price, triple the price. Yeah? Good. So in terms of the data that you're actually using, the question is always, can you distribute the data with lower costs, higher flexibility, higher capacity, and higher performance? So is there something like the techniques that make everything better? And the answer is, surprisingly, to some degree, yes. However, it's not so easy, so there are very complicated techniques usually, and these techniques need new paradigms, right? And sometimes they need a new belief in something that you needed to be, or that you believe to be absolutely necessary, and that in the new systems you believe to be obsolete, right? You don't need it anymore. You don't need to enforce it, right? And we will also talk about this idea of combining different systems or combining different paradigms to get the best of both worlds, usually sacrificing something that you don't need so much, right? There's usually always a sacrifice, of course, right? There's money for nothing does not exist, right? There's always cost. Good. And then there's some additional nice-to-have features. So, for example, unlimited linear scaling, right? If I use parallelization techniques or something like that, I want to have a different effect whether I use 4 machines, 8 machines, 16 machines, or 32 machines. You know, like if it does not scale anymore, then the effect that I have through parallelization does not work. And I want the same for my distributed database system, right? The more nodes I have, the more complicated the administration is, the balancing is, yes, but still the better I can parallelize issues, the better I can use resources, right, that are currently available for something that I need to do anyway. And so this is kind of like unlimited is a big word. Maybe good linear scaling would be more appropriate. Then the schemas. What we see today is that the dream of the global schema, the one schema to rule them all, is not happening, right? In data warehouses, a lot of people were dreaming this dream and were saying, yeah, we need this ETL process, extract, transform, load, right? Where we transform everything into a consistent schema, and then all the data becomes interactionable and exchangeable. However, what you see in companies these days is there's a lot of legacy that is never transformed and that will not be transformed. And even with the new systems that they build, you see them building a lot of legacy of the future, right? You see that decisions are made for some reason because it is necessary at that point of time that does not adhere with the current strategy, with the current overarching global schema kind of strategy, right? More often, what you see is that a lot of the data that is lying around, right, talk about linked open data, talk about data from the web, talk about data from social network, like the data used by Cambridge Analytica these days, right, is there. And of course, that does not adhere to a common schema or to some, because it has never been globalized or never been integrated. Yeah, the integration work is done by clever algorithms, by clever software that have been designed for that, right? So to some degree, you have to loosen up the relational models. Think about things like graph data, like RDF data, linked open data. You know, new types of data that are structured, right? Not yet documents or something like that, full text data, natural language or something like that, but really data that is structured, but the structure is not yet total structure like in the relational sense, like in the this is a table and it is this and this categories and right? Maybe we have to loosen up the relation system a little bit. And then one of the key words that is used very often these days is this idea of elasticity, right? So the infrastructure that you use should grow with the demands that you have, right? If you think about, well, this is maybe very important for the business computer science people, right? If you think about setting up businesses or setting up new profit centers in a company, right? Then the initial investment costs might kill you. You don't have many customers for the thing because it's new, right? You don't know how it will work, or you need to make changes, but you already have to have the full-scale infrastructure for it. That does not work. Basically, the infrastructure has to grow with your demands, with what you're trying to do. And this is the idea of elasticity, right? So you can add machines if you need more computing power. You can take them away if you need less computing power. You can add disk space if you need more, disk space basically, right? And you can remove disks if you don't need the space anymore, if your data becomes less, right? And in a perfect world, it would be in a plug-and-play fashion, you know, like you just go there and say, okay, this is the new drive, flop, works, right? This would be perfect. Talking about distributed data, it has always been a consideration, right? How to manage these things. And during the 80s and 90s, this middleware idea. You put some layer in between, a communication layer, right? And there were a lot of these standards like CORBA. Who has ever heard of CORBA, right? Was a big thing in the 90s. You remember it still, yeah? Everybody was going on, all the business analytics and Price Waterhouse and Accenture and you name them, right? All the consultancy, you need CORBA, you need to invest in CORBA. CORBA stands for Common Object Broker Architecture, right? And the idea was that with all the object-oriented features of languages, of systems these days, you know, you need a middleware component, a broker to handle the objects between applications, right, to build that. Huge efforts were made in that direction, and it was all money for nothing, right? It was all burnt money because it never worked in the end, but there you go. So sometimes it's time for the industry to give back, so maybe it was a good thing, I don't know. Anyway, there are some newer approaches than that. So these middleware approaches of the 80s and 90s were superseded very much by peer-to-peer system, that we still see out there today. So typical things like distributing software in a decentralized fashion, right? Everybody delivers content, but also receives content at the same time. This kind of BitTorrent idea has gone quite big, but also the idea of storing things in a decentralized fashion with multiple copies to allow for a efficient load balancing. That is all peer-to-peer technology, and you still see that today very, very prominent, for example, in the blockchain. The blockchain is just a distributed ledger, no more, no less, right? And the technologies behind that is very similar to what you did in the old peer-to-peer systems beginning of the 2000s, right? On the other hand, the peer-to-peer systems were very clear in sacrificing what made databases. So reintegrating some of the things that make a database usable and useful in the end is definitely necessary. But the basic techniques, the basic technology of peer-to-peer system is really interesting to see as a backbone for these systems, right? So this is where you get the performance improvement in NoSQL systems from, right? And if you connect the peer-to-peer technologies in a clever way with what you actually need in a semantic fashion from your system, then you get one of these new SQL or NoSQL systems that actually might serve your company in a good fashion. Then, recently there's a lot of talk about cloud systems, right? So the idea is very similar to what you do in peer-to-peer, and you see on the cloud conference a lot of the papers that had been written, right, 10 years before on some peer-to-peer conference, you see them in the new guise, right? I mean, there are some other assumptions, but basically it's kind of very similar, right? And you see all the same things like, I don't know, Byzantine agreements that were done for peer-to-peer systems that were initially built for peer-to-peer systems, back in the guise of cloud systems, of distributed systems, right? And you see them occurring more than once. So the idea of a cloud system is of course that you have this obscure cloud with a single point of access, of interaction, and that what happens in the cloud stays in the cloud, you know, like, and you don't see nothing of that. But you just get the access to your data as if from a central point, right? Again, cloud systems sacrifice many database features, but nowadays they are trying to get some of the power back, some of the recoverability, some of the transaction control that was immediately kicked out by the first cloud systems, right? Are now back, and the systems are becoming more stable. The central idea of cloud systems is really this elasticity. Take as much of the cloud as you need and pay as you go, right? Pay only what you need. Don't pay for the whole system in advance, right? So this sharing idea is rather common. So what I want to do for the rest of this lecture is basically focus on peer-to-peer system, or start with peer-to-peer system. And peer-to-peer system have been popularized in a very infamous way, you know, like, I mean, the time was there in the 80s. Personal computers became commonplace, right? So everybody had a computer. In the 70s, it was still the idea. Only big companies have a big mainframe, you know, like, and all the other people work by terminals on that mainframe, right? And then it became clear that the future rather looks distributed, that everybody has a computer who's able to do things, right? We're not talking about terminals here anymore that can do nothing without the mainframe, but we're talking about fat clients here that really can do things in a local fashion and then share things with other computers or other sites. And in 1999, there was Napster, and probably everybody knows what Napster was. Who knows Napster? Who has ever used Napster? Okay, one is honest. Very good. Yeah, I mean, it was the thing, and it was a democratic movement in a way, you know, like, so why not? The idea of Napster was, from a technological viewpoint, a very interesting one. From a legal viewpoint, I mean, we're not lawyers, are we? We are computer science, so we are interested in the technology behind things. And the base problem that Napster was addressing was, how can you share resources within a highly volatile and decentralized networks of independent nodes, right? And these nodes were called peers then. And the idea was that everybody has a computer at home, and all these computers are connected via the web, right, via the internet. And that made for a big computing machinery, a very powerful computing machinery, where you could store things in a decentralized fashion, and everybody contributes to the central storing, and where you could exchange things, compute things in a decentralized fashion, right? And everybody contributes computing resources that are currently not used, right? So the basic idea was a very good one. And the volatility came from, well, since it's personal PCs, right, they're not always running. But you do something and check your email and watch a movie or whatever, and then you turn it off, right? And one of the problems was that you usually turn it off in, okay, now I have to go, right? And not shut it down properly and log out of several networks and finish what you do before you log down, blah, 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 right? But since things are running in a distributed fashion beyond your control on your computer, right? You don't want to control the shutdown process, right? You don't want to wait for some, I'm still down, please wait. No, right? I just want to go, that's it. So the idea to handle a very large number of peers, right? All the computers in the world, basically. Handle this volatility of people joining the web network, people leaving the network, and still providing a stable service during that time. That was at the base, at the heart of peer-to-peer systems, of the first Napster community. And the basic technology that was used, as well as the basic features that were offered, were no transaction control and fail safety and recovery and whatnot, but they first considered only the basics, right? Sharing, nodes dropping out, nodes joining in, efficient computations. That was it. Nothing more, right? And a peer-to-peer network as such is a virtual overlay for the sharing of these resources. And the idea of virtual is kind of that you do have the classical internet topology, how things are really connected in the real world, via LANs and wireless access points and so on. And the data is actually shipped. But this infrastructure is not what you want to consider when you have a certain application in mind, right? Basically, I don't care whether my emails are routed via the US before they arrive in the office that is just next door, right? Many of them actually are. And you ask yourself, well, is that a sensible thing? Well, if you have a common ground or a common task to perform, then maybe shipping everything via a third country is not a good idea because it takes longer. On the other hand, why should I care? So why can't I say, well, with all these nice messenger services, right, the Skype and the you name it, right, I do have a direct connection, and whether this direct connection is somehow reflected in the actual network by a complete path, a complex path, is none of my concerns. Logically, virtually, I do have this direct connection. How it is established in the physical world, not my problem. Problem of Lars Wolf. He does these things, right? I don't care. I'm working here. So this is the beauty of working in the higher OSI layers, right? You can always say, no, this is all semantics. We don't care about how it works nitty-gritty, right? This is Lars Wolf or something. Yeah? So good thing. Good. So the virtual overlay was, of course, IP-based. So you had a way of recognizing machines, and you had a way of routing the information that should be a direct link on a network layer that was a little bit more complex than what you thought. In any way, since you wanted to do something with it, share resources, share, well, basically music at that point, but still, right, share storage space or share computing power, right? You wanted the thing to be decentralized, the sharing idea, and to be self-organizing, right? You don't want it to care in a manual sense whether somebody dropped out or not, whether there was a hole in the network. It should be resilient against people dropping out. It should be resilient against people joining, Well, at least to some degree, right? You should have a connected network such that no single peer is a single point of failure. Because if that would drop out, the network would be split, right? Which is not what you would want. This idea of self-organization became pretty big, and more often than not, biological systems were used as a model for self-organization, right? How cells grow, or how swarm intelligence and all that kind of stuff, right? So a lot of the technologies that were then introduced in computer science were actually based on real-world biological systems, right? Interesting. Still, the peers can transfer data via this direct link that, in fact, physically is not a direct link, but who cares? And there were some enabling technologies that were the personal computers, everybody had one at home, right? And high-speed internet, so you didn't have to wait. The direct connection that you were simulating was not hampered by the actual physical transfer, right? So when we all had 65K modems or something like that, right? Things could get rather sticky before you got some data from some other location, right? But as soon as that improved, it was much better. The challenges that peer-to-peer networks are facing is kind of like, how do you discover resources, right? How do you find anything in that network in a query sense, right? Then how do you organize that network? No single points of failures. Alternative routes, right? If some route breaks down. Handshakes, so that if your file transfer, only legal stuff, of course, breaks off, right? That it is handed at that point over to some other peer, and not you have to start again, right? You have to start all over again. And then the actual transfer of the data, how is that managed? Good. The first thing was the computers, basically, right? And if you look at the development of terminal capabilities, then going back to 1992, right? We came out of the 80s. In the 80s, the personal computer, the PC, was invented, right? No more mainframes and terminals, but everybody had his own PC. One of the first computers, Commodore 64, who knows about that still? No, you're too young, right? We all had one at those days in the 80s, right? And it was a new thing. It was actually built here in Braunschweig for the German distribution, so kind of interesting. But even in the 90s, so the average hard drive disk was 300 megabytes, right? The clock frequency, 100 megahertz. This is what your cell phone loves at, right? 2002, 10 years later, we go to 100 gigabytes. Much nicer, right? And the personal computers have capabilities that are comparable to high-end servers, to the mainframe of the 80s, right? So 20 years later, 15 years later, what you have in your pocket is more powerful what they had in the big banks and insurance companies. The entire company infrastructure in your pocket. It's mind-boggling if you think about it. So 2007, average clock frequency 3 gigahertz, average hard disk size 320 gigabyte. You see it developing, faster and faster and faster. You get more, you get more, you get more. More processing power, more disk space, and so on. Same with the internet connectivity, right? Early 1990s, this was the 56K modems, right? Took for ages until something arrived, right? End of the 90s, first broadband connections to your house. I mean, universities and so on had broadband earlier. There was the Datenautobahn and stuff like that, right? But still, now you have it in your house. Everybody has it. Cable modems up to 10 megabits per second. End of the 90s, introduction of DSL, ADSL, and so on. Deregulation of the telephone market. Before there was all telecom, and telecom was not really interested in new investments because they were monopolists, right? So why should they build something that is faster if it costs money, right? Money that they get anyway from the customers, even with bad service. And when they deregulated, private competition came into the market, and they had to move. They had to do something, right? In the 2000s, bandwidth is not a problem anymore, right? So transferring the data is kind of like very cheap. And even though the data became bigger and bigger and bigger, right? So in the 90s, it was MP3 was the format that made it for the first time possible to transfer data like a complete album of some artist, right, in acceptable time, right? Nowadays, we don't want MP3 anymore. We want lossless audio, you know, like all these files, because we just have the bandwidth, you know. We don't care anymore. Same with the movies, you know, like where you started in small digital devices in the 90s, right? With small movies and very low resolution. Now you want high definition, blah, whatever, yeah. So the data gets bigger too, and you always have to put things into perspective. The more storage space that we have, the more bandwidth that we have, the more data we will figure out we need, right? So it's not that we are at a point of saturation where we say, okay, this is enough bandwidth. We can always need more, right? And the market is always there for improvement. So to get towards the classification of the peer-to-peer system, the first thing that occurred end of the 90s was really the Napster, right? And the Napster was for file sharing. Let's put it like that, right? And this was also the idea, let's share information. Whether that was in a democratic sense or whether that was in an illegal sense is a topic that was often discussed. However, it made changes to the industry. I mean, that's just what has to be said for Napster, right? The recording industry would never have moved, and things like iTunes and Spotify or what you have today, right? All these digital revolution things would never have happened probably if they did not see it's not working anymore the way they are used to have it work, right? I mean, there were for 100 years they were setting on recording devices like records or CDs or whatever, right? And now all this digital stuff comes along, right? You know, like they were just not moving fast enough. What also can be shared, bandwidth, right? This idea of can we get a new Linux distribution faster to a lot of people using just the same network than everybody does an individual download, or these BitTorrent ideas, right? Everybody distributes, everybody balances the load in the network and uses parts of the network that are not used at the moment. Then storage space, or these network attached storage or storage area networks, right? That were built for putting things in different areas. For example, resilience against dropouts of the networks, or resilience against earthquakes or stuff like that. If it's distributed, parts of it are safe, right? And if it's replicated in the distribution, all of the data is safe, right? Or at least the interaction has to be massive until something goes haywire. And then, of course, computing power. The idea of all the different high-performance computing settings share the computing power that you don't use at the moment, and somebody else might use it for whatever. Now that we do Bitcoin mining, sharing computing power is a big thing again, right? So it's kind of interesting. So, and that brings us to our last detour for today. A course in file sharing.
File sharing, yeah. I think this is a milestone in peer-to-peer computing. As it was already mentioned, 1999, that was the year that Napster came into the game. And I don't know how many of you know the story, but basically there was a couple of guys who were actually talking about sharing. This idea of sharing was actually already there, but not in the form that they were thinking about. Because if you go back to the first internet services, you have these IRC channels to share stuff, share files. It was possible. But this, 1999, was the first time that someone was saying, well, maybe it's just about making people to share what they love. In this case, they started cleverly with music, MP3 files. And it's not only about saying, look, this is what you can download from me, but it's about saying, well, this is what you can download from me, and so on. So you have a lot of people actually doing it. And they were quite successful. I mean, it was really in the news. And it was a simple model. We will cover the model in details in our future lectures. But basically, they just have a single application where there was some centralized index of the users and the list of files that you can download. And basically what was happening at the beginning is that you were just saying, hey, I'm here and I have these files to share. And when somebody was actually looking for something, typing in a query, what was basically happening is at the beginning, this centralized server will say, okay, these are the users and these are the files that you're looking for. This is where you can actually start your download. And then you will just do these overlay connections and the download will start just that easy. Because it was so easy, actually, it was so popular that in many campuses, in many university campuses, this application was forbidden before any legal issues, actually, because it was consuming a lot of bandwidth. And the thing is that just as fast as they go into the news and they were very famous and there was a lot of bright new ideas behind this, at the same speed they were actually shut down by the industry, by the digital copyright industry, and they were lead to a first largest scale legal issues that stopped them from functioning. But the thing that happened to Napster actually is that they allowed some others to follow up on the ideas. And then Nutella and Gaza came into the game as well, now saying, okay, music was very nice, but what if we add movies, videos, games, right? So people can actually share all of that. And they innovate in a way this second generation of peer-to-peer, because they said, okay, let's forget about this centralized idea because that might stop us from continuing working. And then, but still they have some problems, and you can see that another generation came into the game as well, as Freenet. This is the idea where you have decentralized approach, but trying to preserve the anonymity of the users because you don't want the users to get into legal issues. And the idea was there. It was very, very successful, and very quickly BitTorrent came into the game with this protocol that we will cover in one of the lectures, and basically relying on this idea of very efficiently delivering a lot of data. And this is one of the core things that allows some other applications. In particular, the distribution of software and updates. And there are some examples, for instance, in 2008, I don't know how many of you know this game, World of Warcraft. But back in 2008, they had to distribute basically roughly 3 gigabytes. They have to patch the game to millions of users. And the most efficient way to do it was actually using BitTorrent as a protocol. And it was very efficient, and it was a very nice example that some other people follow up after that. So you have several Linux distributions actually doing that, relying on this paradigm, this technology to do it. Even Microsoft, I don't know how many of you know, but Windows 10 was actually doing exactly the same idea. And it's very powerful. You don't depend on a centralized way to download so much data, but you distribute it in a clever way. And you will see when we cover in the lecture this idea of distributed hash tables, why we say that is a very efficient way to deliver a lot of data. And exactly the same point of using peer-to-peer was behind some other kinds of applications. One of them is Skype. And at the time that they built the application, I mean, just saying, well, it's not only about sharing music and videos, you know, it's about getting people to communicate to each other in a very efficient way, not too expensive. First, it was this idea of using video conferencing. And actually, Skype was relying on the same idea of Napster, with this centralized server that facilitates how to locate the users. But at the end, after the connection was done, it was through the peers that all this communication was happening, and in a very, very efficient way. So you see another example that why peer-to-peer was just some very hot topic that many people will argue began in the 1990 with Napster and sort of stopped in 2008 in a way, in the traditional way that we see it. But just to give some numbers, in 2006, it was estimated that 70% of the traffic was actually due to peer-to-peer. And what you can actually see from this graph is how this traffic was actually distributed among the different kinds of applications. Right here you have the web. I mean, this is roughly 2010. And you see how the web was declining in favor of peer-to-peer. But right here, I mean, just having the technology available and the limitation of imagining some other kinds of applications, you start seeing that now the traffic was more onto video. And this is when you have, for instance, Netflix and YouTube. And when you start seeing some other kinds of things happening that led to the idea of cloud storage, actually, to enable some web age applications. I can go on because I think it's on 2 slides. So after you saw all this peer-to-peer paradigm and all the things that they were facilitating, so there was this need that in web applications that were actually growing very fast, and they needed computational power and storage. And the truth is that what happened at that time in 2008, just the main problem that you had at that time, that it was too expensive to do it in a traditional way, it was too inflexible, and Google, Amazon, and Yahoo, they saw an opportunity on this problem. And they say, okay, look at what was happening in the last few years. We have peer-to-peer technology, very efficient. We have this idea of distributed databases. What if with our infrastructure, we combine those two things and we create in favor of cheap, large-scale data centers that can allow web applications to scale without any problems. And this is exactly what they started to do. I mean, what you observe in this image is some kind of desktop computers. I mean, you see these ugly things over here, but they are servers, actually, from one of these big players on cloud storage today. So they were focusing on low-end hardware that allows to basically whenever I put new machines, it will add something to what I have in terms of storage, in terms of power capabilities. And this is what they were trying to do at that point. It's 2008, 2009, and it was all about the cloud. And why that happened is because of these phenomena, web applications. In this slide, we see the example of Facebook, social networking. Today, it has more than 2 billion users, active users. It's a lot of users. And you see in the plot how it started, and it's a plot in terms of millions of users and how they start to grow and grow and grow. And if you think about the numbers, and I have to say I like numbers, so I will give you some other numbers here about Facebook. If you look at the numbers and you think, okay, how do they do it? Just 2 billion users. And you might say, are they active users? Yes. On average, you have 1.4 billion people doing something on Facebook. In fact, as we just talked and we just keep the lines on the slides, you got 5 new profiles created every second on Facebook. You got people like, just in Europe, 300 million people using Facebook very actively. You have photo uploads, 300 million per day. That's a lot. just thinking about what happens in just 1 minute. 500,000 of comments posted, more than 250,000 updated, and a lot of photos going up. Of course, you have these fake profiles, but I mean, this is how it is. But still, if you look at the numbers, these are numbers that makes you think, okay, how do they keep on providing the service? How do they do that? And if you add to that the fact that they provide some entertainment inside of Facebook, this is a very nice example of these web applications that just grow so fast that you need to rely on this kind of infrastructure that can only be a reality, that an application that was founded, I don't know how many of you know about this game, Farmville. 2009 it was created. A very simple game. It's just farm management. That means plowing land, growing crops, harvesting crops and trees. That was the game, 2009. 2 years, and it was the app that was most used on Facebook. Look at his peak in 2010, 30 million users. The challenge here is, as we put it here in the slide, reads and writes, quite a lot. So how do you support these kinds of applications? How do you do it? The answer is you need large-scale data centers. And here are some other numbers for you. Talking again about Facebook, how do they do it? Look, for instance, in 2009, 30,000 servers. And you just look 3 years after that, and they basically exponentially grow in the number of servers they were using to provide the service. The same goes for Microsoft. Just to support the search engine Bing, you have 80,000 servers. Yahoo, the same stuff, 100,000 servers. The same goes for Amazon, eBay. And the question is, so how do you build these large-scale data centers? And as it turned out, one of the big players, which is Google, they revealed some information to try to understand what they were actually doing to support some huge demand of applications. Because whenever you think about Google and going online and putting some keywords and hitting enter, you just don't wait anything. You instantly see some results. And so how do they do it? These large-scale servers, they reveal some information. I mean, it's a little bit old, 2007, 2009. I mean, they keep the information anyways a little bit of, okay, I don't tell you too much. But when they do, it is quite interesting to see what they have learned and how they actually do it. So back in 2007, basically, they were just building their own custom servers. They were not buying out-of-the-box servers. No, they were building their own servers. And that meant at that time more than 1 million servers. And they didn't sell any servers, of course, but they could have been the 4th largest in the whole world. And if you think about the infrastructure behind these data centers to connect them, I mean, they are distributed around the world. You connect them, I mean, at least in 2010, they were saying, well, mostly 7% of all the internet traffic that is connected to the data centers of Google pass through to the data centers of Google, and they are connected to massive fiber lines. That means that 60% of the traffic is connecting directly to consumer networks without connecting to any other global backbone. In other words, if Google were actually an internet service provider, they will be the 3rd largest on earth. That was quite impressive to know these numbers. And so to actually construct and build these data centers, well, you need a lot of money. That's one of the things that we get from these numbers. In 2007, when they revealed these numbers, just to build 4 completely new data centers, there will be $600 million. That was what they said it costed. But if you see it, it's not only about how much do you invest to build the data center. So the operational costs, the estimated operational cost it goes to the $1 billion. That's a lot of money as well. And when you think about another big issue is power consumption. And just to give you an idea, one of the largest data centers of Google at that time in 2007 was consuming half of the power that is needed to cover all the needs from Brownsville. That's quite a lot as well. And if we go deep to see, so how do these servers look like? So this is what they had at that time. Basically, they have, let's put it like this, commodity hardware, as they call it, basically outdated hardware in racks of 40, 50 of them, putting them together, no big deal, just with its own 12 volts battery, and in a simple container like this. I mean, there is a link here to a video if you want to take a look at some of this stuff that they were doing at that time. So what you can observe from this is, okay, 40 to 80 of these things are the racks and outdated hardware. And they have millions of them. So that means that they are very, 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 very unstable. This is a fact, and this is something that they share with the community. And they were always arguing, yes, but they are very cheap. Instead of buying these millions of servers to a server provider, it will be much more expensive than doing it like this. And what they share, what they have learned is, yes, it is unstable. And in just 1 year, for just one new cluster, which is made of several racks, these are some of the numbers that they share of the problems that they have. If you think about it, you can divide the problems in 3 different categories. You can say, well, one of the main problems might be power consumption, power failures. That's one problem. Second type of problem will be the interconnections between the racks and the different components to make the network the network, routers and the net wiring connections as well. And the third category will be the machines itself. I mean, these are outdated machines, they will fail. They will have problems in the hard disk. Actually, they share some statistics about that every 3 months they have to substitute completely new hard disk for many machines. And if you think about these 3 categories, just to give you some examples, just a simple overheating will go down machines in less than 5 minutes, and it will take a couple of days to make them back. Quite interesting. Then if you have a power distribution unit failure, that means up to 1,000 of machines will go away suddenly. They will disappear, as I said. And it will take you some time, maybe half a day to come back. The same goes with the other type of failures. They might have this network rewiring, this rack movement, because they keep on growing. So these things happen, and they expect this to happen, and they know, they have measured what are the problems that they have. 500,000 machines, up to 1,000 machines down, another 6 hours. Then you can say, if you go to the specific aspects of the network maintenance, routers, failures, you still have this, in summary, a lot of problems. A lot of machines will disappear, and it will take you time to make them back. The machine itself, I mean, 1,000 individual machines, they will have problems, different kinds of problems, yes, and thousands of hard drives will just die. So, in summary, lots of problems, lots. And the question is, so how do you deal with this when your goal is to provide 100% of service, roughly? This is what you want to provide. No data or almost no data loss. How do you do it? And of course, you want to have the maintenance cost to the minimum. This is one of the goals as the company. And the solution to that is software. Google built their own file system, the Google file system. They built their own, based on this file system, they built what they call at the beginning Bigtable, Google Bigtable, that was substituted by Cloud Spanner, which we will cover in a couple of weeks. So basically, they designed this software to deal with these kinds of issues and being responsive 100% of the time, almost 100% of the time with the services they were providing. Just to give you some examples, what this Google file system means and this kind of new paradigm in programming to process massive amounts of data. This is some information from 2006, for instance. If you think about building just the index, Google can do that with MapReduce, which is part of the software stack that they develop and they open source at the end, the design. And you need to, for doing the indexing, to process 500 petabytes a month in 2006, roughly 300,000 jobs distributed over all these data centers. And this paradigm is actually the same that the other big competitors are using. So think about Yahoo and this Yahoo Map service that they have. They do MapReduce jobs as well, but they use the open source Apache implementation, which is called Hadoop, but it's relying on the same model. The same goes to Facebook. If you were wondering how they do it, when I update my profile and instantly everyone can see it, they are processing a lot of data and they do it using this kind of new paradigm, relying on this technology. So this is how they actually manage to cope with these very demanding kinds of applications. So I think it's just 2 more. Can I go? Okay, yeah. So in summary, what we wanted to actually share with you today is that we will cover 3 major distributed topics on the lecture. One is distributed databases. This is kind of the classical approach to data distribution. We will discuss full database features in a distributed manner, so we will visit transactions, query language schemas, and we will see that they have some limitations, and some of them we mentioned today in the lecture: flexibility, this idea of elasticity, and being able to scale, especially for the kinds of applications that we just mentioned during the tour. We will cover peer-to-peer in detail as well, so we will actually do these algorithms that are behind distributed hash tables and how they manage to do decentralized use on PCs to actually go to the other kind of extreme when you compare to databases. And then we will cover cloud storage and non-SQL systems. We will cover some aspects of Cassandra, CouchDB, and HBase that actually what they are trying to do is to do a compromise between these 2 words that we will explore at the beginning: databases, peer-to-peer. And I think this picture summarizes very well what we are going to do in the lecture, because if you see in the x-axis over here, you have the database features, and this is something that have championed very well distributed databases. They have a lot of these features. We are talking about transactions, storage guarantees, and so on. And on the other hand, we have in the y-axis network features, this idea of scalability. This is something that peer-to-peer show to have a lot. And what we saw starting from 2008 and up to now is this idea of the cloud and putting these 2 things together to be able to provide some of these databases capabilities with the flexibility of the peer-to-peer networking. So this is basically what we will do in our lecture. And if there are not questions, what we will do next week is actually starting with the database work and doing data partitioning and sharding. So if there is no questions, I guess this will be the end of the lecture of today. So thank you for your attention. Yeah.